Hi, Bowen.
Hi, Liu Jun.
Hi, how are you?
Good.
Do you want to try to share the screen?
Yeah, let me try it. Actually, is this good?
Yes.
Yeah, long time no see. So I guess it's
Ah,
morning in Singapore.
yes. I think the last time we saw each other was still in 2017. Oh,
That's a spirit
ah,
entanglement entropy paper.
I see.
Yeah.
So last December, you also went to Hong Kong. One day, some people had dinner with you, but that day I couldn't join.
But in a different university.
Yeah. Maybe let's get started. So I will start recording and I will introduce you and then Bowen, you can start.
Recording in progress.
Okay. Is also the topic today. In this entanglement bootstrap program, the goal is to use some entanglement structures in the ground state of a topological phase to extract the universal physics of the topological phase. Ever since this idea was proposed in 2019, I
Would be about entanglement bootstrap. It's a pretty big research program, and it's also ongoing. So a lot of open problems and puzzles. So if you look at my title, expensive, but it still is a very physically meaningful problem. That's why I want to spend most of my talk motivate the related problems and try to just towards the end of the talk, I sketch some ways to make progress. And okay, the outline of my talk is the following. First, I would like to briefly have everyone on the same page by introducing what is entanglement bootstrap and the recent update. So my worldview of this program. And second, I would introduce some physical motivation for considering robust version of the entanglement bootstrap. Some are related to no-go theorem, related to the chiral quantum state in 2 dimensions, and there are easy to state, so I want to mention that. And yeah, in the end, we talk about some ways to make progress. All right. So what is the entanglement bootstrap? Let me motivate this way. So many of us are interested in quantum many-body system, like condensed matter system, and many of you are probably also interested in quantum information. But one of the fascinating thing about many-body system is that the interaction between the qubits or the local degree of freedom can have interesting physical phenomena emerges at low energy, at large length scales. Yeah, of course, nowadays people also think about finite temperature, mixed state. Yeah, those are all can be considered. Our local Hamiltonian, and in the large length scale, suppose the Hamiltonian is hard to solve, then we can propose the effective field theory, like guess the Lagrangian of the quantum field theory and to make predictions. That's a very fruitful approach. And more recently, we can talk about entanglement. In a qubit, they are entangled in some way. We can take a subsystem A and the complement B. And if we have a quantum state, we can ask what's the entanglement, how the regions are entangled. And one thing you can consider is the entanglement entropy. And that's not even the only thing you can consider. There are other measures of entanglement. And we can also distinguish the 3 different approaches by the length scales. The length scale of the local Hamiltonian is a microscopic length scale, the smallest length scale. And the field theory emerges at a really large length scale. That's the IR, microscopic length scale. But for the entanglement, one nice thing about it is that you can choose a small and large qubit. So not only that, you can think about the fixed point. You have some ability to like look at the system in different length scale, so that the flow of the system at a different length scale can be perved if you'd like to do numeric. Sometimes you have the ability to do that. That's a good thing.
Sorry, Bowen, I have a question.
Yeah.
Why do you distinguish the Hamiltonian approach and wave function approach? They look almost as microscopic as each other to me.
Good question. I think in a few pages I will have some idea. Like in entanglement, we can block the region, the size of the region to pretty large. That's what I'm trying to see. And another difference is that the wave function here, like a ground state, it has strictly less information of the original Hamiltonian, right?
Okay.
Yeah.
Thanks.
Thanks for the question. Okay. Yeah, let me talk in slightly more detail about bipartite entanglement. So suppose we have pure state. Of course, we can choose our favorite orthonormal basis, write the state in a simple way, and the reduced density matrix is this. You can compute trace rho log rho, that's the entanglement entropy. Well, you can also consider Renyi entropy, but this one is my favorite for some reasons, like a strong subadditivity applied to the Neumann entropy. It will be useful later. But now let's consider a physical system of a two-dimensional gap state system. What I mean is that we have two-dimensional space. Imagine you have many qubits spread on this two-dimensional plane. There is one well-known entanglement area law. The name can be confusing for someone who haven't heard about it because the area in the two dimension means the length of the boundary of A. So that's the length of the circle. That's the leading term, and the subleading term gamma is assumed to be a constant. In with the physical system, gamma is a constant depending on the topology. Okay. Now let's play with the entropy. So entropy of a single region is something to consider, but there are even more physical quantities can be obtained by doing a linear combination of entropy, like SA plus SC minus SAC. That's known as the mutual information. And if we take A, B, C, like this partition of a two-dimensional plane, then in many physical systems, the mutual information just decay exponentially with the width of B. Okay, so if you make a log plot, it's like this, and that's interesting. And if you do another more longer combination with A, B, and C, yeah, this one has 4 terms. This is known as a conditional mutual information. It's somewhat more harder to understand, but intuitively, that's the information shared between A and C with the knowledge of B. So suppose we know B very well, then the knowledge shared with A and C could be different value than we don't have B. So those are 2 different quantities, but in gap two-dimensional system, what we usually see is that this thing also decay exponentially with the width. but there's some interesting caveat. So in some system, the decay might be slower, like a power law or something.
Sorry, Bowen, may I ask a question? Here, when you're calculating the conditional mutual information, the condition area B is just a part of the buffer regime, right?
Exactly. Yeah, this is a
Yeah, sure. I could imagine that if you take B as the whole buffer regime, here then the exponent if the conditional mutual information still decay, then the length scale defined from here is exactly the Markov length proposed by Shengqi and Tim.
Oh, good. Yeah, that's exactly true.
Sure. That's I probably think that you made a claim that sometimes decay more slowly than the mutual information. Probably emphasize that there might be some global correlation between A and C that is not intermediate by B. Am I right? My intuition is right.
Right. Currently, I'm not making a theoretical explanation. I'm just pointing out some evidence, numerical finding that when B is a disk like this one, rather than like an annulus, the case you are saying, if we consider the second case, usually the conditional mutual information is larger. So yeah, we can consider the conditional mutual information for both of the cases, but somehow. The second one seemed to be larger in some of the models. The decay is lower, I mean.
Thanks a lot.
So in the example where it decays slowly, what is the example?
Mm.
Is it a ground state of some gap local Hamiltonian?
Good. Yeah, here I'm mentioning the example I learned from Xiang Li, John McGreevy's student. He was doing the P plus IP superconductor. He was exploring the parameter, like a parameter space of the Hamiltonian. We found that for some parameter space, value of the parameter, it decay more like a power law, but for other parameter, more like a exponential decay.
I see. So this conditional mutual information is the difference between two mutual information. And the mutual information can be, there's an upper bound of the mutual information set by the correlation function times the log of the correlation function. And there's a lower bound of the mutual information set by the correlation function itself. So maybe these two bounds can be used to prove some behavior of the conditional mutual information.
Good point. That's also my hope. Although in practice, I feel like knowing the exponential decay of a correlation function is still pretty well. We cannot immediately use that fact to derive the decay of mutual information and conditional mutual information in two dimensions. In 1D, people made some progress.
I need to think about it, but the upper bound and lower bound I just mentioned applies to all dimensions. Also,
Yeah.
it applies to mixed states.
Right. Yeah, I think I know the bound you talk about.
And there are two bounds. There's an upper bound and the lower bound. The lower bound is the lower bound of the mutual information is given by the correlation function. The upper bound is given by the correlation function times the log of the correlation function.
Oh, I see. Yeah, maybe you can tell me about the one with the logs afterwards.
Yeah, sure.
Thank you. Okay, yeah. So I'm mainly mentioning some empirical fact to get started. Yeah, just to get some idea on the correlations of the two-dimensional gap system. And now, yeah, we can talk about a more interesting term. So that's related to system with anions. So when there are anions in the system, it turns out the subleading term gamma is actually very meaningful. So it's count as the two very famous reference in around the year 2005. They point out that the subleading term should give you the total quantum dimension of the anion. That's a counting of anions. So if there's no anions in the system, you get 0. And if there are anions, you get some positive number. And the arguments are based on either topological quantum field theory or a class of solvable Hamiltonian, with a nice string net wave function. So in either case, they can argue that gamma give you this nice value. Okay, so that's some basic thing to talk about. Now let me start to do some more interesting thing. So let me ask a question. Kind of a warm-up question. I suppose I tell you some system has two properties, group A and group B. Yeah, all of them, both of them are related to the entanglement entropy of the ground state. So which one is more interesting as a physical law? Yeah, anyone want to try? Okay, let me tell you my answer. So my answer will be group A because it contains some interesting number. So it's not 0, but the group B on the right-hand side, you just get 0. Seems boring, right? So it contains more information. So I would say group A is more interesting. But let me ask another question. So which one seems like a promising foundation of a physical theory? Right? Well, by physical theory, I mean we try to really develop our understanding, try to explain things. So in that case, I would say I like group B better for the same reason, because it contains less information. Yeah, the idea is that if you don't have that information, then like the gamma term is not there. This equation gamma equal to log d is not in the starting point. That means you want to explain it, right? Suppose you can do that, and then that's great. So I would say B is better. Any objections? Oh, I received a message. Okay, so I guess this question is for Liu Jun. Okay, I think I just go ahead. The host may answer the question in the chat. Okay. So more generally, yeah, what I'm trying to say that it's a distinctions. There is an interesting distinctions between physical laws and physical theory, and this is from this TED talk, which I liked a lot. So roughly speaking, physical laws is about what happens, and physical theory is about why it happens. So we try to come up with the most logical explanation of it. Yeah, there's definitely some difference. And for instance, Kepler had the 3 laws about planet motion, right? But that's not the end of the story, because those 3 laws will be explained more simply in Newton's theory of gravity. Yeah, so that's an example of the difference. And what is entanglement bootstrap? I would say that we want to come up with the most logical explanation of why things happens. The people may already, at least in the context of 2 plus 1D, the context of Anyon theory, many people had written the so-called modular tensor category, that the thing that describes the how anyons work. But now what we try to do is to get some really simple looking starting point and start from there. We want to derive everything. So everything must be followed just from some simple principle. And in fact, the axiom, the starting point we identify is almost structureless. So that's how I like this research program. And here I'd like to do a comparison with the conformal bootstrap, which explains why we would like to call this entanglement bootstrap. The reason is that this is our theory is about constraint. So we start from some very abstract we function with put some conditions without requiring too much, but then we constrain various different type of things, and we exclude the different possibility, and what's left are the things that yeah, some structure we can prove. Then we can define anyons, fusion of anyons, string operators, and also derive the formula of topological entanglement entropy, and so on. Yeah, roughly that's what we do. And in more detail.
Excuse me. There's indeed a question in the chat.
Okay, wait. Let me see. What's the analog between group A and B? I guess that's the question. The analog between group A and B. So let me first go back. Analog. Oh, yeah, I guess both are something you can compute from the ground state. So you have a linear combination of entropy, yeah, for different regions. That's the similarity. And the difference is that the topology of the regions are different, such that if you do the plus and minus of the entanglement entropy, you left with some constant term. I hope that answers the question. Okay, great. Okay, now let me go into slightly more detail. So I should say this is well, some axiom is more like a mathematician flavored condition, but I will try to explain the physics. But yeah, well, I won't give much examples, but let me say for the moment that in the two-dimensional state, you can think about your favorite gap state, like a Chern insulator, P plus Fp superconductor, and toric code, and some fractional quantum Hall state. Yeah, you can choose any of your favorite wave function, and then I will say, okay, because of the area law, we expect conditions like those two will be satisfied on each little ball of the wave function. So the wave function is really large, but we just take bounded radius balls covered the entire plane. We require some simple condition on each of the balls. That's our starting point. Intuitively, that's some kind of a fixed point condition. We will only expect this to hold on large enough length scale. So like we zoom out to large enough length scale, and hope the error will decay. And to prove anything, we had to, at least in our original paper, we had to assume that the right-hand side vanishes exactly. So we have exact zero on the right-hand side, but the physical intuition is what I said. And more generally, this is a kind of a fixed point condition advocated in the paper by David Lin and John McGreevy. They were thinking about conformal field theory, which is a more general setup. So later on we realized that those can be, there's some more general version of this. But let me say this is a kind of a gapped fixed point. Okay. And here is some slightly more intuition. So suppose I said that the two conditions are on small length scale. So then you may ask, suppose we zoom out to some larger length scale. So can we just start from the larger length scale? It turns out the answer is yes, because the axioms on the small length scale plus the strong subadditivity condition, a general condition for tripartite quantum C. From there, you can show that the same condition hold on much larger disks. So we can as well start from a larger length scale. So there is a sense that we are talking about RG fixed point. And as you may ask another question, suppose we pick a random state, any state in the Hilbert space. What happens to the two conditions? It turns out that you won't have a. Let me go to the previous page. If you take an arbitrary state, the right-hand side won't be zero. It will be always greater or equal to zero. Right. So in that sense, we seem to propose that the nature, the vacuum of the 2D gap state looks like a kind of like an extreme. The more general state will give you larger values, but those conditions drop to the minimal for the like a vacuum state of the 2D system. Then let me try to make some derivation using the axiom, because the axioms are just area law. So everyone would agree those seems reasonable, but what can we do with it? And it turns out they can be used in some simple ways. First, let me consider a state with a partition A, B, C, and D, meaning that we have a large system, and A, B, and C each has enough number of qubits, meaning that the systems are large enough. Then the condition axiom A1 says that the combination I call it delta, will be zero. by strong subadditivity. This very famous condition on any tripartite state, SAB plus SBC plus, greater or equal to SB plus SABC. This powerful condition tells you that delta given upper bound of I, and therefore the conditional mutual information must be 0. So the axiom A1 in fact tells you that there are a lot of quantum Markov state in the ground state. Yeah, of course it depends on the partition, but there is a large class of such partition you can draw. Good. And the next thing is to identify some structures. It turns out the good idea is to consider a topologically non-trivial region. But the region is much larger, well, not much larger, but several times larger than the ball that we impose the axiom A0 and A1, the two area log assumption. Yeah, those are the little balls, but now the annulus I draw is wider than them. And by using the axiom and the constraint from the quantum Markov state, it turns out we can constrain the convex set of density matrices on such annuli. And we can show that the convex set is more like a simplex, which can store classical information rather than like a block sphere, rather than like things you can store quantum information. And the intuition behind this simplex is that now we can explain the extreme point as state obtained by pushing an anion string across the annulus. So yeah, indeed, in our framework, we first have the we first prove, based on the state of the quantum Markov state and other quantum information property of the state, the multipartite state. We prove the simplex theorem, and then we define anion that way. And in the end, we can also show the existence of a string operator that creates the anions. Yeah, that's how we build the anion theory using a wave function. And it's like a analog to the study of dancing patterns of ants. So ants are small things, and they interact with each other in somewhat simple ways. But if you have a lot of them, yeah, you can find very interesting emergent phenomena. And this aspect is very similar to what we do here, because we are keep talking about small balls, and how the small balls are, yeah, related to the rest of the system. It turns out from there we can understand what's going on in much larger length scale. And I guess I didn't talk about breeding, but let me just mention it briefly. So for breeding, we can consider locally embedded region in the background, and we can identify the state lives on this locally embedded region. The interesting thing about it is that the global state living on this immersed region can't be simultaneously obtain the vacuum on annulus X and Y. So they must be talking to each other in non-trivial way. And that's a key point. And with that, we can fill in the rest of the proof and show the breeding must be non-degenerate for the anion theory. And okay. Right. So another intuition I want to convey before I move to the approximate case was the fact that we can deform the region in topological way. So there is an important isomorphism theorem saying if the region, all the regions are embedded in some background. So if the region omega 0 can be smoothly deformed to region omega 1, then the information convex set of them are isomorphic. So that's why we don't need to talk about the shapes of the region. We just talk about whether it's annulus or anything. So we can talk about equivalent classes of the region, and yeah, and what information can be encoded in such region. Yeah, that's the idea. And actually, how do we move the region? The idea is that we can partition the region like the ABC. Yeah, they are very small. I hope you can see the letters A, B, and C. And now imagine we have a convex set of density matrices AB. It turns out how do we move the region around? We just do it by elementary step. Channel defined from the reference state. Yeah, we can map the convex set to another convex set, and to map back, we can do a partial trace. So in that way, it turns out the convex set are isomorphic. That's a non-trivial statement. And now, yeah, and you get the intuition. Then when I draw the deformation of the regions, you should think of that way. We just add a little region somewhere, and then do a partial trace somewhere else. So that it moved little by bit. Then you can do large deformation by with those small steps. I would like also to comment on the fact that the things from entanglement is a big deal, and this is from a lecture by Feynman in the 1960s. He gave it at Cornell. I liked it very much. Most of the about seeking new law, I think it's still very interesting. If you would like to watch it. One sentence he said was, so like any schemes like think of physical law, symmetry laws are known to everybody, and they try it all the time. So yeah, if you get stuck, that must be another way next time. And indeed, in most of the previous century, there are so many progress related to symmetry. Like think about symmetry law, whether it's a space-time, it's a gauge theory, or spontaneous symmetry breaking, conservation laws. From symmetry, a lot of good ideas. But there are some clause, it's like the fractional quantum Hall, the system, a thermal Hall, or a system with anions. The system that the robust properties are still there, even if you break the microscopic symmetry. So I feel like using entanglement is another new idea which might last for many years. We will see. But some of you may argue there are some other idea using generalized symmetry. But I guess what entanglement bootstrap is doing seems to be very at the basic level. Even the generalized symmetry, the thing can emerge from entanglement. That's my point of view. Okay. Since we made progress, understand the anions, we wanted to generalize the framework to different contexts. So we also considered gapped boundaries and 3D. We can write down similar axioms because such systems also have some sort of area law. We just try to find the combination of entropy that are the most fundamental and try to make derivations from there. So far, such approach looks successful, and we even identify some objects that are, to our knowledge, not listed in the category theory paper. We call it parton in gapped domain wall, and some are but not in 3D. and we are talking to some category people to make a dictionary between what we predict in entanglement bootstrap and in category theory. Another fascinating project I was doing with the people, John McGreevy student, especially with gapless boundaries, and we guessed some new other assumption because this was kind of unexpected to me because this is beyond area law. Yeah, I struggled with this, but it turns out we made some progress recently. Okay, so far that's my review of entanglement bootstrap, and now I'm going to explain some physical motivation to consider the so-called robust entanglement bootstrap. If you have questions in the previous session, you please ask. Okay. Yeah. Then let me continue. To understand why it's worthwhile to have a robust entanglement bootstrap. In other words, to consider errors of the axiom. We don't need to understand a whole lot. So let me give a much briefer overview of some aspect of entanglement bootstrap. So yeah, let's look at this very nice configuration of a topological entanglement entropy. So if you have this annulus, you partition this into A, B, and C, then you can compute the subleading term using this conditional mutual information. And from there, if you use the strong subadditivity, you immediately find that gamma cannot be too small. The exponential of gamma cannot be smaller than 1. What entanglement bootstrap wanted to do was that we start from a stronger condition. So rather than the general state, we have those two conditions on any 7-side block of this coarse-grained lattice. So if those two conditions are satisfied, it turns out we can constrain the value of gamma much better. So yeah, we can recover the gamma is the sum of total quantum dimension, that type of thing. Just use the entanglement area law, even without telling you what effective field theory could describe the system. So it's purely something about the quantum many-body system itself. Then we can make progress, constrain such values. Another thing to mention is that it's about information. It's about from this wave function. If we look at the subsystem, what type of information can we extract? So like on the torus, we can show that the information of locally indistinguishable density matrices are fully coherent, and on an annulus, the resulting information can be seen. It is like a simplex with an orthogonal extreme point. And if you have access to only a disk, then you have no information. So every state reduced to the same thing. And this sounds familiar because it's related to the quantum error correcting condition. And now below I will talk about some ways to violate the axiom. So one thing is the spurious contribution. First discussed by Bravi and first appeared on arXiv in Liu Jun's paper with Junwang. The idea was, suppose you have some clean state like a toric code ground state or even product state. Within finite depth circuits, there's some strange state with the most strange subleading terms. how does entanglement bootstrap think about such state? It turns out such state violate one of the axiom. So now you may say this is a worry of the framework. Can we deal with that? The answer is yes. So we have several ways to deal with them. So one way is that you can modify the axiom A1 into another condition, which manifestly deal with the spurious contribution. So it's more like in geometry, in Euclidean geometry, you can either choose to work with the frame with the orthogonal axes x and y, or you can more generally you can directly work with a frame that don't have orthogonal axes. So this approach is like a very direct way to deal with the violation of A1. But there is another nice way to deal with errors, which is more like you have some nice frame, but you can rotate it into another frame. You always have the freedom to do that by removing the circuit. At least this works for any known examples of such spurious contribution. The claim is that if you rotate a state set 0 to another state set 1, both of them are satisfied A0 and A1. It turned out the subleading term computed from any such state must be the same. So this would be already good enough to me, in the sense that now we can claim that the whatever subleading term we compute from entanglement bootstrap state must be the same value. So it's a universal property of the phase. This point could be somewhat subtle. So if you have questions, please ask.
Can you just repeat it?
Right. So what I just said was, suppose you have a state set 1, which is related to another state set 0 by a finite depth circuit. And suppose both of the states satisfy both of the axioms of entanglement bootstrap. Then we can show that the subleading term must be the same, and that's a reliable answer. So it's the correct subleading term.
But this relies on the assumption that both of them do satisfy the two axioms.
Yeah. So the idea is that sometimes you get a state with spurious contribution. Then let's test the two axioms. Then you find one of them is violated. Then you please don't trust the answer. And we that's the idea. Yeah, but the other way, the more direct way to deal with the states is also quite interesting. So this version of the axiom with a circuit invariant. So that's some good things about it.
Yeah. So let me be a little bit more picky. So this is saying, suppose the states satisfy the axioms, then gamma and J are invariant on the finite depth quantum circuit. I still suppose they satisfy the two axioms. Then are they invariant on the time evolution, finite duration time evolution generated by local Hamiltonians?
By local Hamiltonian, that I cannot see for sure. For example, I think you can come up with some weird Hamiltonian that map the state set 0 to set theta. Then you know that set theta, you have a spurious modular commutator as described by Julian Gass and Michael Levin.
Okay.
Yeah, okay. My point is that there's some obvious violation, but in some sense we still have some good understanding about it. But now let me go to another type of violation.
Just to clarify, the reason I ask this question is because I think using finite depth quantum circuit is a bit too restrictive. If we use a time evolution generated by local Hamiltonian over a finite period, that may be more physical.
Right. So in that way you can generate the local circuit with tails, right?
Yeah.
Yeah. Yeah, that
So
is a
if there are such tails, can one still conclude that gamma 0 and gamma 1, J0 and J1 are the same?
that's a good question. So that's related to dealing with error. So I would say that's part of a robust entanglement bootstrap. So and that haven't been developed yet.
I see.
Good. And okay, great. Now yeah, some of the important motivation for go beyond the exact area law are for chiral phases. But let me first show you some data for the P plus IP, which actually suggests the error of the axiom decay pretty fast when we go to large length scale. So this is a P plus IP superconductor. Yeah, we look at the subsystem of different sizes. And if we scale to rescale of the whole thing or rescale of the subsystem, then the error of A0 and A1 in this case decays exponentially. And in fact we also made some heuristic argument to guess a pretty nice formula about chiral central charge. So on the wave function in this work in collaboration with Ada Kim, Gatar Kato, and Victor Albert, we argue that this formula, so you take a tripartite of the ground state wave function, consider the commutator of the entanglement Hamiltonian or modular Hamiltonian. So it's a log reduced density matrix of rho on two different regions. The answer should be pi over 3 C minus. So yeah, if you look at the paper, you will find that we argue that the quantum Markov state structure of the gap the ground state was the reason that we can first of all we can deform the region without changing the value of J. And the pi over 3 prefactor is also argued theoretically, assuming that we can chop the reduced density matrix, the logarithmic of the density matrix into pieces. So the modular Hamiltonian is local based on the area law. Then we correctly predict the factor pi over 3, correct in the sense that later on the numerical test verified this prefactor. So we were quite happy about it, and in fact like a few months after this success, I was in this thing. I was very happy and think, okay, entanglement bootstrap seems to be better than the solvable models because it captures chiral state. In fact, it's not quite true yet because of some no-go theorem I'm going to sketch. But essentially, what we were able to see very concretely was that suppose you have a 2D quantum state on those coarse-grained lattice, and suppose each coarse-grained lattice site has a finite dimensional Hilbert space. Then the exact area law. So suppose you have the right-hand side of the axiom to be exactly 0. Then that it's impossible to have chiral response of the system. So what does that imply on the previous figure I showed you? So previously I showed you this figure that we constrain. We use those entropy conditions to constrain the value of gamma so that SSA excludes the leftmost region. The entanglement bootstrap, the previous papers, exclude the regions in between those interesting numbers. It turns out what the no-go theorem implies is that we are actually excluded more region than we expected, because some of the numbers correspond to chiral anion systems. They have non-trivial chiral response, so that's inconsistent with the exact satisfied axioms. So that's to me this is the most important motivation for going beyond exact entanglement bootstrap.
Question?
Yeah.
And we derive a lower bound of the basically this local theorem is saying if I have a microscopic system where the dimension of the local Hilbert spaces is finite, then if it's chiral, then the correlation length, at least one consequence of this is that the correlation length cannot be zero.
Yeah.
I'd like to ask, can one set some lower bound of the correlation length, given in terms of the chiral central charge and the dimension of the local Hilbert spaces?
Right. Yeah, that's a very interesting question. Yeah. We had some discussion with John McGreevy student. I think David sketched something in last time, and Xiang might had another idea. Yeah, we were chatting this maybe 1.5 years ago, but maybe there's some update. So yeah, but the previous time we chatted, there's some interesting ideas, but we didn't finalize it. Yeah, but yeah, that's a very interesting thing. So what you ask is that whether there is a bound like beyond strict zero, because those two papers are saying, oh, we cannot be exact zero, but now you want to show there's some gap. Yeah, that's a good question.
Yeah.
Yeah, and those two papers use two different approaches, but both of them use the finite dimensional, like the structure of quantum Markov state on finite dimensional Hilbert space. But let me give you a sketch of one of the approach. So this is based on the modular flow, yeah, in this paper, and based on the modular commutator. So the idea is actually pretty simple. So the first idea is modular flow. You have a ground state. We have no Hamiltonian, so we are not doing Hamiltonian evolution. But nonetheless, we can take a region subsystem X. You can do a modular flow with the reduced density matrix on X by some imaginary power. So this thing is a unitary evolution on the state. So we get another normalized state. We can ask, does the entropy of any subsystem changes? So the subsystem I draw several different choices. And as you may guess from the chirality that we need some asymmetric, like not symmetric choice of the subsystems, like the yellow one, the pink one, yeah, they give you some non-zero numbers actually proportional to the modular commutator. But for other regions, the entropy are invariant. But now, suppose the exact one satisfy on the ground state, it turns out we can show that the entropy change is at a constant rate. So you can do a finite time modular flow. So put t to any finite number. It turns out we can show that the in larger length scale. But the problem is that I don't see how. And of course, people can also hope to make progress in the opposite direction by constructing some state with let's see, some constant violation of A1 by a small amount, like something below log2 and go 0.01. Can you make such a spurious state with tiny violation of A1? If we succeed, then we can disprove the conjecture. That's also interesting. But to my knowledge, we don't know such counterexample yet. So all right. So despite the fact there are yeah interesting problems that are hard to solve, we would like to pick some simpler problem to get some experience, and this is an ongoing work I'm doing with Isaac Kim. The opportunity to do that with the fact that I stayed in UC Davis last summer for 3 months, so we chatted in person, and I learned a lot of tools to deal with errors from Isaac. And yeah, for simplicity, we consider the torus or any closed manifold in 2-dimension filled with coarse-grained lattice. We ask, suppose the axioms have errors, do we still have a coherent state space emergent from the area law? Yeah, that's a problem. And in slight more detail, in fact, I won't go into much detail. I just have 2 slides to go. So in more details, we have a closed manifold, which is let's say it's a torus filled with a hexagons, those coarse-grained lattice, each contain enough qubit. We have m of such cells, and each cell has a d-dimensional Hilbert space, and the violation of the axioms are delta 0 and delta 1. And suppose we take the reference state such that the violations are those numbers, and furthermore, we need an assumption, well, not an assumption, a condition called stable entropy condition. That's saying if we relax the local density matrix of the reference state, the entropy doesn't go up too much. Controlled by epsilon and the number of qubits of the system. And why do we consider this condition? This is because, first of all, on any disk, such condition must be true. And second, for any abelian annual model on the torus, this condition also holds and can be showed explicitly. But more general is unclear, but we need this condition. But the intuition is kind of the reference state we choose are the give state. So we kind of we consider a finite temperature give state and we cool it down to almost 0 temperature. Then we end up with a mixture of different ground states. Yeah, that one should have this property. That's the intuition. And start from there. Then we relax the convex set a little bit. So we introduce some error epsilon to the locally reduced density matrix. What we can show is that with some mild relaxation of the errors, we end up with a convex set with some coherent Hilbert space. And a byproduct of the analysis is that the entropy of the reference state must be approximately quantized. So if we take the exponential of the entropy, we are, this can be integers, but the non-integer value will be forbidden by some bound. Yeah, that's a sketch of the progress. And thank you.
Okay, thank you, Bowen, for the very interesting talk. Any other questions?
What is the motivation for this approximate area law to begin with? I sort of missed that part.
Okay, good. Let me recall some of the motivations. So I guess one thing is that we, I'm like a well, I'm interested in condensed matter, and most of the lattice models are on finite dimensional local Hilbert space. And the local theorem here, even before those papers, people seem to have the intuition that chiral state seem to hard to find the exactly solvable models. Like commuting projector model doesn't work. Frustration-free model doesn't seem to work. So it's like on lattice there should be finite correlation links and convert to entanglement bootstrap. That means that the axiom on the right-hand side shouldn't be exactly zero. The theorem we proved previously in our original paper under the assumption that the axiom that the right-hand side must be zero. Yeah, but we want to know whether the theorem we prove are robust. So yeah, we want to develop some tools so that we have the robust version of it. Yeah, that's the main motivation.
I think one of the main technical points that is used in the entanglement bootstrap is to use the condition for quantum Markov chain based on the
Yeah, like the structure theorem of quantum Markov state. Like rho ABC, if it's a Markov state, it's a sum of the left hand times the right hand with the some nice decomposition into left and right. They are supported on B in some orthogonal subspace. And for chiral state, we don't have that. And indeed, when I was talking about this toy problem, yeah, we are dealing with, we didn't use the Markov state structure. Yeah, we use something else.
But you know that there are also papers on these approximate Markov states, right? So
Yes.
you say something different. Is it more on the line of these approximate Markov state, or it's completely just not using this Markov property from the conditional mutual information?
The answer is I think we will use it, and yeah, I think I know some. I think the papers you mentioned are some approximate quantum Markov state on tripartite state. Like what can we say? Like recovery is not perfect but almost perfect. It's the recovery fidelity is bounded by something related to conditional mutual information. Yeah, that type of thing. Those are useful quantum information tools. And now we want to study the manifold system, like apply the quantum information technique to this manifold system. That's some non-trivial things steps going on here. So yeah, ultimately we certainly we will use this result. And for the toy problem, we have use some bound on the mutual information, but to go further, like to deal with subsystem, the regions with boundary, yeah, we will use them. Yeah, I believe we will use them.
Thank you.
Any other questions? Okay, do you have any idea to extend all these things to mixed states?
Yeah, that's a very good question. Yeah, indeed, I'm working on some problem on mixed state, and in fact, yeah, let me go here. Yeah. Yeah, then I cheated a little bit because those two figures are just I copied from the ongoing project about mixed state. So you see, I didn't write the axiom A0 and A1 rather I said the mutual information conditional mutual information vanishes And those two conditions hold for volume loss state as well. And this one, that's some kind of a version of this one also give you a topological constant for mixed state. In fact, you can just copy this piece and develop your own theory of mixed state.
Uh-huh.
Yeah.
Yeah, that's interesting. Any other questions? Okay, if not, we will thank Bowen for the very interesting talk. Thank you. So I will stop recording and we can leave Zoom.
Recording stopped.
Thanks, everyone.